Okay, we can hear you. That's great. Tom has just confirmed that he can hear me. That's great. All right, so lots of things can go wrong, and hopefully not will go wrong with this kind of experiment, because there's so many components that need to work, and doing this as a live broadcast also makes it even more complicated, because I'm using a new software that I'm not familiar with. But hopefully we will overcome those difficulties, and if you guys are a bit patient with me, I will hopefully be able to do this. I can operate this software remotely here, and I can you know, change the size of images and things here, so it should be pretty good. Just waiting for a few minutes to see if we get any more viewers coming on here, but it doesn't really matter, because if somebody misses the beginning, they can always wind back and check it out later. So the first thing I'm going to do here is I'm going to go over to the FICS-Fusion reactor over there, and I'm going to run through the various components and explain the machine a little bit in detail for those of you who aren't familiar with it. And maybe if you have any questions, I won't be able to see the chat from over there because I have to switch cameras. So if you would just bear with me for a minute, I'm going to do that right now. I'm going to turn on the other audio source as well. And let's have a look. Let's be a little bit patient with me then. Patient with me. Right. Now I think you should be able to hear me over the vacuum pumps and all that. So just so you hear, this is the FICS-Fusion rig. Now let's have a look at the individual components. One thing I should mention is that to anybody who's thinking of building a fusion reactor, it's really important to consider safety ahead of everything else. So when you start building, start thinking about safety first. So in this case, well, I started with a welded metal frame with the intention of building all the high voltage into a Faraday cage. And this Faraday cage and the whole frame is grounded with a big heavy copper wire that goes into a ground rod. So that's one of the critical things. And the cage doors have interlocks, which little switches here on the door, which will cut off the high voltage power supply if anybody inadvertently opens the door. The other issue with safety is neutrons and X-rays. So in this case we have a remote control on all the high voltage and vacuum devices, and that's run from a small lab jack, which I'll go to later. And the other thing we concern ourselves about is X-rays, and I've just recently added here an extra little LED shield here on the side, which shields that area over there where I sit, because the only area where X-rays can come out is along these glass discs, because we're using ordinary float glass and not the LED glass. All right, so this is the actual FICS-Fusion reactor, and this is a ground potential down here. This is a high voltage break, and this is what I refer to as the head. And inside the head here we have the source and the drain. The source goes to the high voltage power supply. The source goes to the high voltage power supply, and the drain goes to the Zener diode. So the objective here is that we want to set up a high voltage potential between the source and the drain, and create a plasma which is essentially floating at low potential, or at minus 40 to 50 kilovolts. All right. Now we need to, in order for this to work, I need to admit the gas, the deuterium gas, into the cathode at minus 40 to 50,000 kilovolts. So to do that, I have this object here, which I call a gas elevator, and that is at normal pressure, that is at atmospheric pressure with deuterium gas, and it has over here a tap and a small leak, 3 micron hole leak, which then leaks into the chamber with deuterium. And this was Frank Sand's idea to run this at atmospheric pressure, and that works brilliantly. Thank you, Frank. Okay, now to create a voltage differential between the source and the drain is connected via a Zener diode, which is a homemade job here. And that can be, I can set that Zener diode to between 40 and 60 kilovolts. At the moment, I have set it to 40 kilovolts for this experiment because it's summer here in Sydney and quite humid. And I'm concerned that if we push it beyond 40, 45 kilovolts, that we might get some arcs, unwanted arcs, and that's always bad news, and causes various kinds of sparks which upset the electronics. So the Zener diode, so many of you might wonder, where do you get a 40 kilovolt Zener diode from? Well, you make it yourself. So inside here, this is a PVC tube with 3 layers. So the outside layer has got cooling water because it gets quite hot. And at the top here, where the high voltage is connected, there's a high voltage cable, and I'm not sure if you can see in there, but there is dielectric oil and circuit boards with hundreds of Zener diodes, and they're in series, and I can plug a little banana plug in to change the voltage from 40 to 45 to 50, etc. Okay, this is the deuterium gas supply. It comes in there through the regulator, and I just admit a little bit of gas there, and that's enough for weeks of operation. Goes into the gas elevator, goes across here to the tap, which I have to remember to open at some point, and through that little leak valve and into the cathode. Now there is this tiny little viewport here. I haven't been able to look in through it because I haven't had a camera attached, but I tried to rig up something today here with a temporary camera, so I'll see if that works, but don't count on it. Now, as all of you know, we need good vacuum, so down here I have a JVac rotary vacuum pump, and for some reason this camera keeps going dark on me, and a Varian turbo pump which is running at the moment, and this is the turbo controller. Okay. Over here we have the high voltage power supply, and it's more than powerful enough for what I need. It goes to about 125 kilovolts and 10 milliamps, so at the moment we won't go beyond 40 kilovolts, and I think I have it set here to, I'll set it to about 5 milliamps, which should be sufficient for today's run. Now at the bottom here are the electronics. This is all in a steel cabinet, and most of the electronics will run off the 2 rechargeable batteries, which you can see on the left hand side there. And what you see in the middle down here, if I can just hold this here, down the bottom there we have a USB hub which is optically connected to my computer over there. And from the USB we have the lab jack, which is the lab jack U3 high voltage, and which is the data acquisition module which acquires the various inputs and outputs that we need to run the machine. And right at the back corner there you can see the gamma spectacular that's operating the neutron detector, and it's using the David Housley Schmidt trigger to connect to the Russian SN19 detector. Alright, so I think that covers most of it. I have a little microphone, a little loudspeaker there that occasionally clicks when background neutrons come past. If you look around the corner here, if my camera will stretch, you can see around the corner here, that is the neutron detector. And the distance between the neutron detector and the head is 45 centimeters, for those who want to work that out. And yeah, that's pretty much the rig. So I might go back to my computer and start preparing this for a short run and see if we can get any neutrons. Sorry about the shaky camera because I'm trying to talk and hold this thing at the same time. So let's unplug this and go back to the computer. Can you hear me now, hopefully? I'll turn that off now. Microscope, I can turn that on, you see that? It's not showing up yet. Okay, what about my browser? Okay, we're back to the browser here. And we see the chart. So what we're seeing here now is the vacuum pressure. The vacuum pressure in the chamber, 0.3 millitorr roughly. I don't know how accurate that is. Hang on a second, Tom sent me a message here. Yeah, Tom, I just went through the safety precautions there a moment ago. I hope you got that. Yes, so other safety precautions Tom's asking me about is I have a Victorian ion chamber here which will warn me of any X-rays. So it should be, I've tested this before and I'm fine sitting here, there's no X-rays over here. So I think we are just about ready to start moving on with the experiment. We'll go and make some preparation, and we'd just like to get that webcam working though, that other microscope camera. I wonder why that is not working. I think we got that now. Oh yes, here we go. Okay, so that's better. No, this is the viewport there we can see on the side. I don't know whether it's going to be any interesting or not because that's just something new I just tried today. But we can give it a shot. Right, so I'm going to use my little procedure here and start getting this ready here. Okay. Put that microphone over there so I can grab it later. Turning my the old Deuterium Neutron detector sometimes. This is something of me. High voltage power is on. Okay, I'll turn it off again. Turn on the deuterium. So deuterium is on. The leak valve leaking in the chamber. High voltage is on. Vacuum is on. Cage is closed. Power up the electronics, turn on the vacuum gauge, we've done that. Turn on the neutron detector amplifier, turn up the lab jack, we've done that. Remote the vacuum, less than 1. Open the deuterium valve, I've done that. Turn on the power supply, turn on the neutron detector, turn on the ion chamber, activated the high voltage, and we should be ready to rock and roll. I've got a little list here. Okay, so this is the critical part because now we're going to start slowly increasing the high voltage, and this is where the electronics can crash if we get arcs and sparks. So I have to do this really very carefully. So I'm going to come up here so we can see what we're doing. Okay, now I also want to record this run. So this dashboard that you can see on the screen here, this was written by myself and my son Eric, and also help from Tom. And It records the lab jack, and it works really well with the lab jack, and it's got like these 5 channels, 5 input channels and 2 output channels. It's all coded in Python, and it will run on pretty much any computer, and I can provide a link so that you guys can download it from GitHub. It's pretty good, and the lab jack is only a $150 device, so it's pretty good value. So I'm going to start recording. Now when I start recording, all the charts, everything starts fresh, and we should have everything running here at the moment. Just let me check my neutrons. So the neutrons take a little time to come on. There it comes on there. Now, for those of you not familiar with the neutron counting, the neutron detector has an efficiency of roughly 0.7. Now that means that for every neutron that goes through a cubic centimeter of space, where the detector is, it will measure 0.7 of them. So there, and then we look at the sphere around the reactor core and work out the surface area of the sphere, which is 4 pi r square, and that works out that for every count, for every click in the neutron detector, we count 36,000 neutrons, and that you can see I've set up here in the calibration, which I can't scroll down. But anyway, one click I believe is 36,000. So when you see these huge neutron numbers, 36,000, it means very little. That's pretty much background radiation when you see that number there. So we're certainly looking for something bigger than that when we start running this detector. And occasionally you will see a background click. Let's see how this is going at the moment. Why is it not moving? Oh yeah, there it goes. It's moving. So at the moment it's not counting any neutrons, but what you'll see, once there is a neutron, it'll average over 10 or 20 seconds, and you'll see a bit of a spike there. So there you can see there's a little blip up there, which is a background neutron. That'll become clearer here. So here it is. That's one count, and it gets averaged over a number of seconds. And then you'll see it'll drop down again. There it drops down. So that's pretty much one count, and it's set up there at looked like it was 2,000, but it's actually just one count in the detector. But if this was isotropic emission, which is what we talk about in fusion, we talk about total isotropic emission, that would be about 36,000 neutrons. I hope that's clear. All right, so we are ready. So the first thing I'm going to do here is slowly bring the voltage up. As you can see, this is the input voltage. You can see here on the kilovolts, and I'm going to bring that up very, very slowly. So we're now at 18,000 volts, and with the turbo pump going and the valve fully open, the vacuum pressure is very low, and we're not seeing any breakdown. We're not seeing any Paschen breakdown in the plasma at all. So we will continue to increase this very slowly, and with a bit of luck, no arcs. And so far we're seeing no current. So as long as there's no current, there's also no X-rays and no neutrons. You will see that at some point we will have some current flowing. So we're seeing 0.1 milliamps on the input current at the moment. It could simply be leakage into the air because it's quite humid here in Sydney at the moment. So we're now over 40 kilovolts, so we're over the Zener breakdown voltage. So we're at 45 kilovolts, we're over the Zener breakdown voltage, and I think it's time to slowly start closing the gate valve and allow the pressure to build up a little bit, and we hope that the plasma is going to form in the head and not in the core of the reactor. So the leak valve is very small, so it doesn't do all that much. Are you seeing anything? So closing the gate now. Not sure what the pressure is. 0.8, 0.9. We're certainly seeing some more neutrons, a little bit of neutrons, but this is not... We just don't have a plasma yet. It'll happen at some point. Oh, there we go. So that was too much. It broke down completely there. So I'm going to lower the pressure again. Just be patient because it's quite sensitive to. I'll try to increase the voltage a bit. Need a bit of differential at the head. About 50. There's. So, what we're looking for okay, I'm seeing some neutrons, but this is not, it's not burning in the right place. We can see there's no current on the zener. No current on the zener at the moment, which is kind of strange. Okay. So the voltage went straight back down. What we want to see here is we want to see this dial here, which is the yellow output milliamps. We want to see that reading about the same as the input milliamps. So for some reason it's not wanting to do it today. We're certainly in the right region here. Not sure why it's not. Okay. Let me just turn this right back down again. I'm going to just check a couple of things to see if we missed anything. Yeah, everything looks okay. I think we need to just try it one more time. It's possible that our pressure is a bit too low, maybe. So I'm coming up here, closing the gate valve again. I might try starting it a bit lower and then with higher pressure and see if that gives a better result. I went over again. Yeah, I'm sorry about this. We've had this working the other day in a better mode, and it should have worked. At about 45 kilovolts, we should get a current through the zener, and we're not getting that today for some reason. Which means we're not getting formation of plasma between the source and the drain. It should start happening about here. 45 kilovolts. It should be 5 kilovolts over the, and it's not happening. It's happening in the bottom part of the chamber. Which is not what I want. Try increasing the voltage a bit, but I think that'll just make it worse. I'm just not seeing any current going through the output today. Very tricky. So at this voltage and this pressure, you should see it discharge through the zener. Something's not playing ball today. It's doing something, and it's making some neutrons. So if we look at the neutrons here, we can see there's definitely something happening. But this is not the right mode. We should be seeing a current on this dial here, which is just not working for me today. Okay, we're going too high there. I heard a couple of sparks there. I wonder if there's something wrong, because I'm not seeing any current through the zener at all, and we should definitely be seeing some current go to ground through the zeners. It's just not happening. I wonder why that is. Nothing at all. I mean, whether it could be a faulty connection or because I would be happy to see like 2 or 3 milliamps on the input current, and then maybe 2 to 3 on the output current, and then a decent number of neutrons would be good. What are we getting here? So the neutrons are not even over 100,000, which is really very, very, very minimal. What I would expect here is, probably 300,000 neutrons to 500,000 neutrons a second at these type of voltages. So we don't need to go any higher, but that's just not working the way I want it to today. One of the two possibilities: either the output current is a faulty connection over there, or something else is wrong. Alright guys, I'm going to have to go and investigate what the problem is, and schedule something for another day, I think. Neutrons, 60,000, nothing really. This is really this is only 2 or 3 counts, maybe 1 count a second or something. It's nothing. 2 counts a second. And that's not what we're looking for. Just give me a couple of minutes to make a few checks. If you want to sit around and look for a second, I'll see if I can find something. So I've got everything turned off there. So what I've done now is I've just connected the high voltage power supply directly to the Zener diode, so we can do a quick check to see whether the meters are working. So this won't produce any X-rays or neutrons. It just simply puts the power straight into the Zener and across. So you'll see how well the Zener knee works here. I've set it to about 50 kilovolts. So we go here to 50, and then we can see, okay, at 53 kilovolts, its current is draining through the Zener, so it's coming in through the power supply on the green dial, and it's going out through the Zener on the yellow dial. So we now confirm that the Zener is working, and that the breakdown voltage that I've set it to there is 50 kilovolts. That's pretty much exactly right. I mean, it's pretty amazing considering that there's hundreds of Zeners. And you can see there at 52, it just comes straight out there and goes. Okay, so we're all good with that. So if I connect that back onto the reactor, let's have a look. Okay, turn that off. I use a metal wire to discharge the cathode before I put my fingers in there, for obvious reasons. Okay, let's give that one more try before we give up today. Okay, we have power. Okay, so I'm going to ramp that slowly up there. And I'm going to go to, we had a breakdown there before at 53. So let's set it to somewhere around there, 54 kilovolts. We're all good here. We see no X-rays here at the moment. Now we'll slowly ramp up this and see if we will get a breakdown. Going slowly up there. I'm seeing almost something on the yellow dial. Yeah, we're seeing something on the yellow dial there. Not seeing any plasma on the camera there, but just going to wait a second there. We've got 0.2 and 0.1. No X-rays over here, that's good. Getting a little bit of arcs over there. I'm going to bring the voltage down a bit. Okay, we're getting current on the yellow dial now. It's quite sensitive. It really is quite sensitive. And I'm getting some sparks over there at the moment. I don't know if you can hear it, but I can hear a couple of little arcs, so I don't like that. Okay, looks like we're doing something here. Okay, 80,000 neutrons. It's a little better. Increase the pressure a little. So the objective here, for, if you guys understand what I'm doing here, is that The output current on the yellow dial is essentially recoverable, whereas in a regular fusion reactor that current is lost as heat in the shell. But here, because we're siphoning it off at the cathode or at the drain, that could technically be used again as straightforward electric power. Okay, so we're running at the moment. The reactor is running. I can't see any plasma in the viewport, so it's running at a pretty low kind of current and pressure. But it is running, and if I can possibly ramp it up a little bit, as long as we don't get that total breakdown, which is that we want. Okay, so here we've got a bit more current, and that should bring up the neutron count. But I'm also getting a significant amount of arcing. And this is going to bring down the electronics, I think. Okay, so that was a breakdown. We went a bit beyond where we should have been. So now what we're seeing is we get a plasma in the lower chamber, which is not what we want. What I might just do... Okay, here we go again. Okay, but we're getting some serious arcs over there. Okay, we're certainly getting more neutrons. We're also getting we're getting a lot of arcs over there at the moment. I'll bring that down. Just turn up the current again. Without standing over the reactor, it's a bit difficult to see where the arcs are coming from. I'm not confident in the neutron count when I'm getting arcs, because that arcs can upset the counter. I'm quite sure. Yeah, too many arcs happening there. I'm going to conclude this experiment today, and yeah, as I said, lots of things can go wrong and will go wrong when you're doing experiments, and this is just one of those. It could be that the humidity in the air is too high today, and this is why we're getting all the arcs. I can't say without identifying exactly which part is arcing, but it seems when we go to 55, 60 kilovolts that we're getting some breakdown over there in the air, which is not what we want. We definitely want to see that plasma happening in the head. But I'm confident that we'll get this to work, and hopefully see you soon with a much more successful experiment. Thanks for watching.